One of our most popular use cases is around a paradigm that we call the funnel engine. In it, we have a large amount of data that's sitting outside the server, and we're going to filter it as it passes into the server and host memory. The POC that we did is called the intersection algorithm. In this POC, we have two unsorted arrays sitting in storage that we're going to pull out, filter, and find the common elements in both arrays on the FPGA, and then store it into host memory. That compares to pulling all the data into the host memory and running the same algorithm in software.
This intersection benchmark was created by Lu Yang, our CAPI lead in China. In database operations, it's quite typical to pull multiple large data sets from storage and then have software perform a filtering operation on the data in order to find the small amount of data that's actually of interest to the query. There are two problems with this operation. First, with the cost of host memory at a premium, you are filling your local storage with data that you aren't interested in. And second, you're pulling large amounts of data across your PCIe link, which can take quite a bit of time for large data sets. By combining the I/O retrieval with the data filtering on the I/O, we hypothesized that you'll gain in three ways. First, the FPGA will perform the filtering much faster than the processor. Second, you'll send less data across the PCIe, saving time. And third, you'll only load host memory with the data that you need. This slide shows the steps in the processor software method of an array intersection operation. We place the array data in the I/O card for this benchmark. For comparison, the time to access the array data from the on-card memory is the same for both cases, software and FPGA. Our software benchmark starts with a host requesting the retrieval of two target data arrays from I/O. The I/O card accesses the arrays, and the full data set is placed in host memory. The software then reads the arrays and performs the intersections before storing the intersection results into host memory. Compare the previous software method to the FPGA intersection process shown here. We still start with the host program kicking off the request to perform the intersection of two arrays that are in the I/O card memory. But rather than sending the data to the host, the FPGA performs the intersection on the card. From there, it stores the results into the same host memory location that the software used, giving the exact same results. For our benchmark, we ran different size arrays and different data intersection hit rates. The different array sizes are shown in the rows on the results table. In green, you see the benchmark results for software, while the FPGA results are in purple. For both cases, we split the time into two parts: data access time and intersection algorithm time. All times are shown in microseconds. The array access time for software is step 2, and the array access time for the FPGA is step 5, corresponding to the steps in the previous two charts. The intersection algorithm time is step 4 for software and step 3 to 4 for FPGA. Sure enough, the FPGA outperforms the software by 4 times or more. You see that the total time is dominated by the intersection algorithm time, but the data access is consistently less, as we are sending only the results across the PCIe bus in the FPGA case. Note that the resolution number data in both cases is always the same. This indicated that the results data matched in both cases on all rows. This benchmark, along with many other samples, can be found in our CAPI Snap GitHub site under example code.